All right, so I think we can start. Thank you everyone for being here, and we're very excited to have Professor Celis speak at our third MD4SG colloquium of the fall semester. And one note, please remember to mute yourself when you're not speaking. You're, of course, free to ask questions during the talk, and we'll also have a dedicated discussion section at the end of the talk. So we'll have about 15-20 minutes to discuss anything you'd like to talk about afterwards, too. Um, so we're very excited to have Elisa Celis be with us today. She's a professor in the Statistics and Data Science Department at Yale University, and she works on problems that arise in the context of the internet and its societal and economic implications. She works with both experiments and theoretical techniques, and her applications include social computing crowdsourcing, data and network science, and mechanism design and algorithms with a current emphasis on fairness and diversity in artificial intelligence and machine learning. Um, so I'll let Professor Celis continue from here and talk to us about mitigating discrimination in online advertising. Thank you.
Great. Thanks so much for the introduction and for having me. I'm excited to be here and talk to you all. So what I'll be talking about today are mechanism design approaches for mitigating discrimination in online ads. If you saw the previous talk, actually in this sequence, it was a beautiful setup that was looking at exactly where and how discrimination can arise and looking at some perhaps legal considerations when looking at online advertising. What I'll do today is talk a little bit about what one interpretation of fairness might mean. So what do we mean by fairness or discrimination in this context? And then going back to the mathematical principles or mechanism design on which online advertising is based, it's basically a more complicated version of a simple a simple auction. So we'll look at what it would mean to think about things like fairness or think about discrimination in this online auction setting, and what kind of mechanism approaches in that setting we can impose to ensure that we're not allowing for these kind of discriminations on a cross-platform level. So with that, I'll get started. This will let me change. There we go. Okay, so there's to start. I just wanted to talk about fairness very briefly, because we generally, when we think of something like fairness, we kind of have this gut reaction: this is fair or this is unfair. But of course, there's many different ways to um, think about what fairness means formally. And this is certainly not an exhaustive list, but you can roughly categorize the way recent discussions on fairness in an algorithmic context look at into different conceptualizations of what fairness might mean. So there's notions of individual fairness, which basically mean that if there are two individuals who are similar, they should have similar outcomes. So if you have, for example, two candidates who are applying for a loan and their profiles are very similar, presumably the loan decision should be similar on both candidates. And then there's other notions of fairness that rely or focus more on group level characteristics. So by groups, I mean social salient attributes such as gender or race or religion. And here, when we talk about group fairness in general, what we want is that group level outcomes are similar. So going back to this loan example, if we have a whole bunch of male applicants and a whole bunch of female applicants, perhaps what we would think of as a notion of group fairness is that the proportion of people across these groups that get a loan are similar. Then there's other notions of causal fairness, which you might have seen. There's a host of very interesting recent work on notions of causal fairness, where um, there's different discussions on where and how group membership characteristics can have causal effects on outcomes, and these effects should not be direct. And then there's, of course, a lot of discussion as to what we mean by direct. And also some recent characterizations of almost economic notions of fairness. Basically, the effort required to reach a good outcome, right? Getting that loan should perhaps be independent of some group membership characteristics. So it should not be a lot harder in terms of time or resources for members of one group to get access to the resource versus another. So of course, again, this is not exhaustive, but just to say there's kind of a wealth of definitions and things that we could consider when talking about fairness. And all of these, of course, are very interesting. There's very strong arguments for these different notions, and in some cases also against various notions. But the other thing to keep in mind is that there's also many impossibility results. So no matter how much we might want to attain a solution that has perhaps aggregated all relevant concepts of fairness, it's unlikely that we're going to be able to do that. There's just fundamental inconsistencies between them. So unfortunately, we can't get all of them, and there's figuring out what the right kind of fairness construct to think about is, of course, a very challenging problem, which I will not answer today. I don't think anyone has a complete answer, but I think this is where there's a lot of importance and a lot of scope for discussion, especially in an interdisciplinary context, as to what makes sense in what domain and for which stakeholders, etc. But so of these, the one I will focus on today is group fairness, in particular because I think this nicely captures some of the legal definitions, or this class of fairness metrics capture some of the legal definitions that apply to, say, the Fair Housing Act, or legal protections against discrimination in jobs, or various other domains. And so it's particularly relevant when we're talking about online advertising, again, in these protected domains of housing, and jobs, etc. So to give an example of what these type of group fairness interpretations might look like, it's on a very high level, something like this. If, say, I have a job and I have applicants, and these applicants happen to be 100 women have applied for my job and 100 men have applied for my job, then legally, if I have hired 10 of those men, I need to have a very good reason to not have also hired at least 8 of those women. Now, what a very good reason is, that gets argued out in court and things like that. So there are exceptions to this rule, but roughly this is what it says. And this is a nice kind of framing, because we can kind of readily see how this might look like some constraints which we could capture algorithmically and impose in any kind of solution that we might want. Of course, these legal definitions and protections don't apply across the board. They apply in certain domains and to certain groups. So it applies, for example, in lending and housing and employment, and it applies to groups such as gender, race, and religion. So these are encoded in various laws. The other place where I think group fairness really makes a lot of sense is when not directly affecting individuals. When we're talking about people, then there's some very strong arguments for concepts such as individual fairness. When we're talking about something like images, now I don't really have to worry about if I'm kind of over-selecting one image over another. An image itself has no inherent characteristic or inherent protections. So that's a place where we can also think of group fairness type of notions. So one kind of a classic example is kind of the Google image CEO problem. A nice paper by Kay et al. In 2015 illustrated this across a variety of occupations, where they looked at the actual percentage, excuse me, they looked at the actual percentage of CEOs in the US, which was approximately 26% female. And then they looked at Google image results and observed that there are only about 11% female CEO images in the top 100 or so results. And they did this across every profession, and whenever an occupation skewed male, the Google image results skewed more male, and whenever the occupation skewed female, in reality, the image results skewed more female. So basically, any of these differences in the actual labor market, those gender stereotypes of the occupation were exacerbated in the Google image results. So in something like this, again, it's a place where there will be no reason why we would not be able to impose some kind of constraints that say, okay, whatever images we show, we would want it to say match the ground truth, or maybe match even something else, maybe 50-50, or whatever it is that, whatever constraints that we would want to impose. Now, in the space of online advertising, you're kind of in this sphere where you fall in both of these categories. You both are, you're looking at people, you're looking at audiences in this lending, housing, employment, etc. space, and you're also looking at ads. So we don't have to, in terms of ad placement, so these kind of these type of entities which are not people. So I think group fairness really makes a lot of sense to think about when discussing what would be the appropriate context. So just to be a little bit more concrete in terms of what I mean by group fairness, we can think of a population, and for simplicity, let's think of some kind of partition across this population into different groups. And we're going to again select some sets. So say this set is the audience that's going to receive some particular type of ad. Then even within group fairness, there's many different definitions one could choose, or different metrics one could use to assess your algorithm or your mechanism. But roughly they all look at, first, just say the number of items or people from each group that ends up being selected. And once you look at that number, then these metrics are basically different functions of that. So equal representation would say, okay, the number has to be exactly equal across all of these groups. And what we saw earlier, this 80% representation rule, is basically a relaxation of that. Right? Or you might want percentages, etc. But they're all functions of basically this vector that's capturing how many people from each group have I actually selected. So the general approach that we will have in mind is, instead of choosing a specific metric, which again is context dependent and there's impossibility results, so that becomes a very difficult question and would potentially change depending on the domain. What we'll think about instead is, are there these high-level constraints that we can place on this vector overall, so that the set that we select, we basically bound how many people from each group can be selected in potential outcomes, and then we'll still maximize our utility. In the case of ads, this will be some notion of revenue or something like that, subject to these constraints. So again, this is something very high level, but it's a nice way to think about these types of problems, and will apply to various domains. So there's kind of a variety of work I've done along with Nishit Vishnu and a bunch of other colleagues and fantastic students that take this approach towards solving various different optimization problems. But today, the particular work I wanted to talk about is what this framework looks like when we try to apply it to addressing this issue of discrimination in online advertising. So this is primarily based on a paper we presented at ICML 2019 this year, along with my colleague Nishit Vishnoy and a fantastic student, NA, who is applying to PhD programs this year. So if you're a faculty member, keep an eye out for his name. He's really a fantastic student. And again, the premise is, and if you were tuned in last for the previous seminar, the premise is really that there's a widespread discrimination in online advertising. This has made it to the news in a variety of, from a variety of studies. Different places have shown that women are less likely to be shown ads for high-paying jobs, even I think like 10 times less likely to be shown ads for high-paying jobs. This is in some cases explicitly by advertisers, but in other cases just a function of the way that Google, Facebook, etc. optimize their platforms. And there's been several lawsuits that either have been settled or are ongoing. There's, I think, recent news from even just a couple of days ago where Facebook announced kind of even more changes that they're making to their platform. But certainly it's in my opinion, and I think in many people's opinion, not enough. They're basically, these changes, what they have done is made it more difficult to explicitly discriminate with according to race or gender or other protected characteristics when posting a job ad, but it doesn't affect the implicit changes in audience that occur just via the platform ad placement optimization engine, because that will have its own biases that are built in. So even if I, as an employer, am committed to trying to recruit a diverse workforce, even if I'm trying to post an ad that will reach broadly across all groups, I can have nothing in my ad that tries to prefer one group over another, yet when I post it through one of these platforms, that ends up happening. And that is what has not yet been addressed appropriately by any of these online companies, as certainly as far as I know. So what I'm getting at here is basically that, yes, discrimination can be due to explicit targeting by malicious advertisers, right? Someone who says, okay, I only want my ad to go to this segment of the population. But it can also happen due to what are called spillover effects from optimization in the ad delivery. And this has been shown by Ali et al. In a recent paper and a variety of other recent works. So again, this is due to market effects. It has to be due to platform predictions about inferences as to what workers want to see. And it has to do also with what demand there is for certain parts of the population. For example, it's been hypothesized that part of the reason why women don't get as many jobs or as many good job ads as men on these platforms is because there's a lot more demand for ad slots on women's screens by advertisers who have nothing to do with jobs. So someone is selling women's clothing. They want to place an ad targeted to women for women's clothing. That's perfectly reasonable. That's perfectly legal. So that takes up a whole bunch of ad slots, say on women's Facebook feeds. And so there's just fewer ad slots available, perhaps, when a job advertisement comes along. So these type of effects can happen. And if we want to make sure that we prevent them, we have to really do something active, right? Preventing explicit discrimination by advertisers won't protect against this, this kind of problem. So let's go back to kind of a very simplified form of how ad delivery happens. And then we're going to build on this to see what we can do about it to prevent these kinds of issues. So let's just think about a single item auction, which is what, again, it's kind of very, very simple, but really these kind of big, huge platforms are kind of more complicated versions of this. So this is kind of a good place to start. So we'll have some number of advertisers, say we have N advertisers, and we might have M types of users. So these are the groups that we're going to end up caring about. And to think about first, we're just going to have a mechanism which is going to decide basically when a user shows up, which advertiser gets to show that user their ad. So user showing up, this user has some particular type. Kind of in the simplest form, you can think of the advertisers as seeing this type, and they each place some bid. They have some value for this particular type of user. And the mechanism looks at all of these bids and they decide two things. They decide the allocation, so who is going to get this particular ad, which ad is going to be seen by this particular user, and how much that advertiser is going to pay for being able to show their ad. So that's X is the allocation and P is the payment that gets made. Now, of course, this is not happening slowly like this. It's not like every time you show up, a whole bunch of advertisers get pulled. There's this V or valuation of the advertisers is specified by kind of a complex process where they specify their target audience, their overall budget, their bidding strategy, things like this, and the platform effectively bids on the behalf of the advertisers and based on these parameters. And we can kind of model this by taking a Bayesian perspective, where each advertiser basically has a distribution of valuations for each type of audience member. So we're going to think of the valuations really as being drawn from distributions. So again, this is a simplifying assumption, but one that can be and is largely used, especially we have a huge amount of historical data, so it's on such platforms, so you can model such things reasonably well. Now, if we want to kind of start getting at this question of discrimination, we have to think about what the audience of each advertiser ends up being. And this is what we call the coverage. So we can say Qij is the probability that advertiser I wins the auction and the user happens to be of type J. Okay, so this is kind of the coverage. And the audience demographics for an advertiser then, which we can split off as Aij, is basically what percentage of the audience happens to be of type J, right? So of the ads that I won, what percentage of them were of users of type J? So in this particular case, say they won these 6 users, and there's 3 types of users. These are the overall demographics. Now the audience again will depend on the valuations, the budget, other advertisers, what users are available in the system, other attributes, etc. So it's a very complex and intertwined system. Now, if we go back to this kind of framework approach of thinking about what type of constraints make sense in this context, if we want to impose some kind of group fairness notion, what we would want are then basically constraints on these AIJs. So upper and lower bounds that ensure that this audience is distributed according to whatever we decide. So for example, if we want equal representation and there's these 3 types, we will ensure that the upper and lower bounds are exactly 1/3 for each advertiser. So that would force these demographic type of constraints. Now, of course, we probably don't want to constrain all advertisers. We probably just want to constrain, again, the ones that are related to protected domains such as lending, employment, housing. And then we also have to think about which type of groups or subpopulations we want to protect and what those exact constraints make sense in this context. But basically we can encode various metrics, various fairness metrics and various constraints in this manner. Now, all this has just focused on, okay, who in terms of demographics is going to see a particular ad. We still have the question of what the platform is trying to optimize, right? So in general, what these platforms optimize is some form of revenue maximization. That's what they're there for. And and basically choosing the right mechanism for revenue maximization, among other objectives, is the core area of mechanism design. And there's some various things that you probably all know. For example, if we want our mechanism to be truthful in this context, then the pricing rule, if you remember, the mechanism has to decide who gets the ad and then how much the advertiser is charged. Well, in this context, the pricing rule is uniquely defined by the allocation rule. So we don't really have to worry about pricing, we just have to worry about allocation. We can kind of defer the pricing problem. And again, without considering, for example, without considering the type of constraints that I just introduced, we can think of what kind of examples of this mechanism might be. So a standard one that I'm sure you've heard of is the second price auction. So in the second price auction, the highest bidder gets it and they pay the second highest price. What's been shown to be optimal here, again, without any type of constraints, is Meyerson's mechanism, which is effectively a second price auction on what are called virtual values. So you have some transformation these valuations, but you kind of allocate according to these. So it roughly still looks like a second price auction, and this has been shown to be revenue optimal. So so let's think about first this standard problem. So we're trying to find the allocation rule. So we can try to phrase this as an optimization problem. So we're trying to find this allocation rule that decides which advertiser gets which ad. We're going to try to maximize the revenue or the expected revenue. And without any other constraints, really the only thing that we have here in relaxed form is that we only have one user. So we can only allocate one item. Again, we're going to relax this, and that can be corrected later. So you can think of this as being a probability distribution across the different advertisers, but we only have one item to allocate here. Now, if we want to add our constraints, we basically have to add these additional lines into our optimization problem that look at the coverage, right, or look at this audience distribution. So I just rearranged what those constraints were before, but again, we have lower bounds and upper bounds on these coverage probabilities of this audience. So this is what the difference in the optimization problem once we have added constraints. Now the question is still, how can we find the optimal allocation rule in this context? Now we can think about kind of these upper bounds and the lower bounds and just look at the dual problem. And if we compare that to the Meyerson problem, we see that we have basically added these alpha and betas. We have kind of these two additional dual type of variables. And what we're going to, and kind of the main question overall is, how can we solve this slightly more complicated problem? So the first, sorry, I clicked on something. Okay, so the first idea that we can have is to think, okay, well, this alpha and beta, really those are what are getting in the way. If we knew what those were, so let's say I kind of by magic know the best alpha star and beta star, then I can really think of them as just as kind of a transformation of these virtual values, and the solution remains the same. So again, if we pretend we know what this optimal alpha star and beta star are, I know that Meyerson's original problem on these basically shifted or reformulated virtual values, that's going to be optimal, right? So this is kind of the first observation, or the first thing that we can say about these results, is that informally, basically there's a shift that happens once we impose these constraints, such that the optimal allocation rule is the same as Meyerson's rule on a shifted set of virtual values. So if you think about this mechanism, basically there is some vector. Now I've basically combined alpha and beta together. You can think of them as a single collective shift. And instead of taking a bid from each user, we take this shifted bid. And similarly, we take kind of Meyerson's rule, except we apply it to the shifted virtual value, and the payment will also have to be shifted accordingly, or shifted back accordingly. So in a sense, the first thing that we observe is that, okay, we can characterize the optimal mechanisms in a nice way by referring back to Meyerson's optimal mechanism. But of course, the question still remains, yes, that's fine, that's great that it looks like this, it looks simply, but what is that shift, right? Because without that shift, we can't actually implement anything. So the question really is, can we find that alpha? It's not easy to find directly, but the next thing that we tried is basically, can we reparameterize And we're going to have to reparameterize both revenue and the coverage, so both the objective and the constraints, as a function of alpha, right? So if we try to do that, this is not convex in either the objective or the constraints. But if we try to do something slightly different, if we try to reparameterize the revenue as a function of Q, then we can kind of split it into these two programs. So in one, we're reparameterizing, so we have revenue as a function of Q. We still have the constraints, the single item constraint. We can also kind of reparameterize in that way. Excuse me. And then on the other side, what we have is now what we're trying to ask is basically, given this solution that has Q, can we use that then on this right-hand side to find the optimal alpha? Now, of course, if we kind of have to look at these two things in conjunction. We can't solve one without the other, or vice versa. But basically, if we had the optimal solution to Q, to this left-hand side, then the right-hand side would give us this solution to the optimal alpha, and this would define our optimal mechanism. So how can we do this collectively? We basically need to solve these two problems, and what one can show is that these two problems have a lot of structure, which we can leverage in a nice way. So if we look at the left-hand side, the objective is concave in Q. The constraints are linear. Having access to this revenue is delta revenue is tricky. So we can't kind of optimize it directly, but we can kind of use alpha. We can use alpha in its place. So what we're going to use is kind of use a temporary alpha that we can then go back and forth for the other side. And on the other side, now the problem is not convex, but we show that there's no saddle points and any local minima is a global minima, and that allows us to again take steps to solve that. So overall, we're basically trying to solve these two problems jointly. Okay, so we're going to basically go back and forth. We have kind of a tentative alpha that allows us to solve the left-hand side, that gives us a tentative Q that allows us to solve the right-hand side, and we can alternate back and forth, and we can show that this will get us to the optimal alpha. Now, how many rounds this will take, that is the real question, and here we have to look at different properties of the distribution, such as what is the minimum coverage, what do these distribution evaluations look like. We need things to be Lipschitz bounded and things like that, but under some kind of natural assumptions that if you look at data, it seems like you can get reasonable parameters for this. This algorithm converges to something close to the optimal mechanism in a reasonable number of steps. And I won't walk you through this equation. It's kind of messy, but it's, again, kind of looking at data, you can at least get a sense of, in your particular case, how long this process might take to attain this optimal alpha. And as we said before, once we have the optimal alpha, then then that gives us the optimal mechanism by just using Myerson's mechanism and the resulting payment rule by shifting the virtual values. So hopefully that gives you kind of a high-level result of the approach. The question is, of course, okay, that's great. This gives you something. You can kind of work on to get an optimal allocation rule that satisfies your distribution requirements in general. But how does this affect the overall auctions or the overall allocation? So towards this, we had some very preliminary empirical results. I think one of the main difficulties in working in this area is that unless you're sitting inside a company, it's very hard to get any real bids or any idea of what is really going on internally. what we did is we looked at the Yahoo A1 data set, which has been out for a while now. It's on keyword searches, but we looked basically at, we took kind of pairs of keywords that had similar bidders bidding on them. So these are effectively competing audiences, and said, what if we wanted to place some constraints on the distribution of which audience gets it there. So that at least lets us get at some idea of some empirical results. I want to be very clear that this is not on demographic based groups. These are interest based groups, and there's certainly a lot more that is left to be decided in terms of analyzing this empirically. But we thought it was important to at least take a look. So what I want, so again, this is kind of a simplified setting, but what I want you to think about here is there's two groups. In terms of the data set, we had a little over 3,000 auctions, and what we were looking at is what happens as we tighten a fairness constraint, where the fairness constraint is just on the lower bound. So a fairness constraint of 0 means it's a completely unconstrained space. And a fairness constraint of 0.5 means that exactly 50% of the audience has to come from each group. For all of our, here we're placing a constraint across the board on all advertisers. So in this particular data set, we see that it's basically pretty flat until maybe 0.25. That basically means that there's not much, there's kind of the audiences are roughly balanced in that all advertisements are at least 1/4 from each demographic group, right? Before that, the constraints don't affect anything. Because if these constraints aren't tight, then we just revert back to Meyerson's optimal mechanism that shifts to 0, basically. And then as you tighten the constraint, of course, when it's kind of 0.5, that would give us, for this fairness metric, that's what we would consider, say, perfect fairness under this definition. Right. So certainly we show that you can do this. This is kind of following what we expect from the theoretical results. We can attain any of these fairness metrics that we want, but it does end up being a pretty significant shift to get it from whatever the existing demographics were to something that we would consider completely balanced. Okay. What was more surprising to us is that even though this is kind of a big shift in terms of what the audience looks like, if you instead look at what the advertiser displacement is, so what is the difference between the distribution that an advertiser gets from the original Meyerson mechanism versus this shifted fairness mechanism, again, the x-axis is the same, and we're basically looking at how do these probability distributions change. The distributions are actually pretty reasonably close. Here we're just recording the TV distance, and oh, what happened to my other? Sorry, I'm missing one slide perhaps, but basically the advertiser distance difference doesn't tend to be much, and what we see is that what that translates into is that the revenue difference also doesn't end up being much. So we're always within some kind of 0.5% in terms of the revenue between what the shifted fair auction would be versus what the original Meyerson mechanism would be. So it seems, again, it's a very very stylized setup. This needs a lot more investigation, but it seems that there's certainly hope for shifting these distributions around without even impacting something like revenue at a significant level. Okay, so just to conclude, a couple of remarks that I wanted to make. So in terms of the this group fairness framework approach, I think this is just a nice way to look at these type of problems, whether it's online advertising or any other problem that you might have, because it's an easy way to translate optimization problems, the way they're usually framed, into a fair counterpoint part, which is also tractable. And you end up with kind of reasonably interesting and fun optimization problems to solve because they have a lot of structure, so there's hope to do something more. But there's still usually some interesting new techniques that have to be developed. But some other things to consider, of course, we still need to work on determining which metrics to use. This is a fundamentally interdisciplinary effort, which I've not gotten to talk about much in this talk, but it's just something that I always want to emphasize, that the technical side, the algorithmic side, is just one component. Of course, if we want to deploy this, if we want to use this in a particular domain, we have to look very carefully at the contextual and intersectional notions of fairness. And we also have to consider the social and technical limitations when deploying these frameworks. So moving to real ad systems or real employment and job ad data would be very important to really test out the efficacy of this work. But hopefully this is a good first start. This is generally for all of these systems. You start with this kind of single item ad auction, and the technology just built on that in various ways. So hopefully this is a start, and it'd be great to talk to all of you, answer any of your questions, and yeah, that's all. Thank you.
Great, thank you so much, Elisa. That was really interesting. And I have a couple of questions, but I wanted to see if anyone else wants to talk about the presentation, or if they have any comments or questions as well. No, okay, I'll start then. I think that was really interesting to think about. You mentioned the idea that it's a great start to think about how to portray to illustrate these constraints in terms of mathematical notation, and but of course we need the help of people working in these industries to understand what exactly do we mean by fairness metrics, what would be the best applicable scenario. And one thing I'm wondering is, how did you choose the lower and upper bounds um, for working with this mechanism? Do you have a sense of what it would be something realistic, or is that something that you could work with in data better? I'm trying to understand, like, how can we think about even like choosing some parameters that would like give us a sense of how these ads really work?
Mm-hmm. Right. So I guess if you want to deploy this, you would really want a particular fairness metric in mind, right? And what's nice about these constraints is that by placing these upper and lower bounds on effectively this vector for each advertiser user type pair, I can specify type of constraints, you're implicitly encoding a variety of metrics. So if I want the 80% rule, that translates into a particular set of constraints. If I want equal opportunity, that translates into a specific set of constraints. So basically, this is kind of a way to encode multiple fairness metrics. Now, you still have to, at the end of the day, you still have to choose a fairness metric, and that gives you your vector, right? That gives you your upper and lower bound vectors. But it's the reason why we wanted to work with it in this framing is that it's a bit more general, right? As opposed to say, okay, this is the specific fairness metric we want, and deploying and developing a solution for that. This basically allows us to have a meta algorithm that works for a variety of different fairness metrics. Now, in terms of the experiments, we just chose something simple, right? We just kind of two people and just the lower bounds. But something similar could also be done. Presumably, there's many different factors at kind of under consideration when these changes are being made at any of these large companies. So what, in that sense, it's also nice in that it's a little bit flexible, in that you could kind of test out a whole bunch of different criteria for your particular data set, and at least very clearly understand what these trade-offs are.
Thank
Did
you.
that answer your question?
Yeah, I think it's really inspiring to really be able to visualize these different trade-offs, and to at least be able to think about how should we deal with them. But yeah, I agree. Some of these decisions are not maybe for computer scientists, but the work is very valuable and just being able to think about them. Yeah.
Mhm.
So if anyone else has any questions, comments, inputs, feel free to jump in.
Hi, I had a question. So, you mentioned that so each user is sorry. So you said each user is of type J, and I guess I was wondering, does type J only refer to one sort of characteristic, like either gender, race, or religion, or can it refer to multiple characteristics and be maybe an interaction uh, between gender or race or religion? And so then, and if that's the case, you would have like multiple um, I guess multiple groupings of type J, and that seems like it'd be hard to enumerate. And so I guess I was just wondering, how would you go about doing that?
Yeah, that's a great question. So, right. So if you want to look at, so here we were kind of purposely vague and just calling it a type. If you want to look at basically intersectional types, you're right in that as it is phrased, it would basically each type would be in an intersectional category. So I am, so for me, I'm female, I'm Latinx, right? And that would be my category. And there would be a different category for someone who is um, female and Black or any other such combination. So what this does allow you to do is, I mean, you then the type of constraints that you have are of course on top of these intersectional categories, which is nice in that you can do that. It's a little bit different than saying, okay, I have some constraints that apply to gender and I have different constraints that apply to race, et cetera, et cetera. The type of results that this gets are more fine-grained, which may or may not be what you want in your particular setting. Um, I think it absolutely makes sense to think about this in a different format. We've not worked that out explicitly, but basically, I'm seeing if I can get to the right slide. But basically, you could add. That was the one I wanted. Basically, you would have to add multiple such additional. So maybe, okay, call this one Q, call another set of constraints S, call another set of constraints, so that you could still frame the optimization problem the same way. I've not tried to work out the solution, but you would have to do it. I don't think it would just straightforwardly generalize. You'd have to do something a little bit more to make sure you're kind of capturing these if you want the constraints to be separate as opposed to having them be intersectional. Does that make sense?
Yeah, it does. Thank you.
We have a question from Fetulak on the group chat that I'm going to read out loud here. The question is, how to initialize the upper and lower bounds? What if the constraints are changing over time or on time?
Yeah, that's a good question. I think in terms of changing over time, I'm in some ways less concerned about the constraints changing over time, because anytime you want to change the the constraints, that's probably a lengthy process that requires some discussion and whatnot. So you'd anyway kind of go back in and say, okay, this is our new policy on group fairness, and then you would change it. So it's while I would certainly expect it to change, and we would want to be able to change, basically you have to solve this optimization problem again. But I think that's kind of the faster and easier thing to do once you have a solution, right? You can do that. It's just a matter of defining it. In terms of initializing them, the first in terms of initializing them, once you have a fairness metric in mind, then in some cases in some cases, it's very easy. If I say I want equal representation, then there's only one set of upper and lower bound constraints that get that for you. So then it's easy. In some cases, there is still a little bit of wiggle room. So if, for example, you have if you have something, trying to think of a simple example, but even something like the 80% rule, you would basically have an additional parameter where I can set to attain an 80% rule, I can set my upper and lower bounds across a range of parameters, and I would satisfy that notion of fairness. So then you would need, basically you need kind of a little wrapper optimization that does some kind of linear search across the potential settings of this parameter. So you're right, I hit some of the details in terms of how to initialize, but generally it's kind of a simple search that you can do by running this optimization problem kind of a few different ways. If you want to look at what that might look like, we spell it out in more detail in a classification paper that's appeared at FATSTAR 2019. So you can look at it by myself, and Nishith Vishnoy, and some of our students. So that one spells that out in a little bit more detail in terms of the initialization.
I had a question about one of the comments you made on, I think, your last slide or second to last slide. It was a general comment on sort of defining appropriate fairness metrics together with the wider community of researchers, especially those perhaps from sociology or other disciplines who might have thought about this from a different perspective. And so I was wondering if you could elaborate a little more on what your views are on helpful ways that computer scientists can engage in this kind of conversation. And as one idea, like you've been mentioning how this particular constraint you have done group fairness here, you chose because it's quite flexible. You can use it to encode a number of definitions of fairness that you can maybe work in conjunction to try a few out. And I think this could be useful both in like legal applications as well as in, there's another example I had in mind, but I forgot. But yeah, I was wondering if you could talk a little about those kinds of conversations.
Yeah, absolutely. I mean, I think it's so important to understand that we are just one piece of the solution, right? And putting these in context and understanding what the right notions of fairness are in context, that's certainly not something that I can do myself in isolation as a computer scientist, and it's not even something that I believe one can do in general. It's just context dependent. It'll depend on the domain. It'll depend on who your user pool is and a variety of other factors. So I think certainly that is one of the reasons why I've been trying to work in this, as you mentioned, this kind of flexible framework type of approach. I think it's a little bit dangerous to, as a community, start working only on kind of very specific agreed upon definitions of fairness, because kind of for two reasons. And if I am a practitioner and I want to deploy something that is useful for my community, I would either have to kind of start from scratch, which means kind of either hire in-house or maybe find someone to consult with, but something very specific to my situation, or I would be forced to use kind of less ideal notions of fairness for my application where I happen to have existing solutions. So certainly whether it's this type of framework approach or something else, but having these type of solutions that work flexibly with a variety of metrics, I think is really important. And it certainly makes life more difficult in some cases, but I would definitely encourage anyone who is really trying to make a broad impact with their work, not just in academia, but beyond that, to consider and look at these type of approaches. In terms of other work, I do think it's also important to try to develop those type of interdisciplinary collaborations. And that's something I've been trying to do more and more over the years. So we have a very recent kind of computation and society initiative that we started at Yale this semester. It's more broad than fairness, but it's basically looking at where can we bring both computational and legal and the social sciences and the business school, everyone together to kind of jointly tackle these problems. And I find it so useful to have these conversations in all directions. I mean, it's both useful. I mean, I've had so many people say, okay, it's useful. It's so useful to know what is possible technically, right? Because the first defense of any one of these companies is like, oh yes, sure, of course we want to not discriminate, but it's just so complicated, it's impossible, right? And you want the people who are sitting in that courtroom, right, or who are sitting in that, or who are parts of the general public to know that no, that's not the case anymore. There are things you can do. I'm not saying it'll be easy, but it's not like it's an impossible solution that no one's even thought about before, right? So kind of both taking the time to communicate with people outside our field to just say, look, this is what we've already done. This is what is possible, and there's more things that we can do. And then, of course, for me also, I just learned so much hearing from people who have grappled with these very complicated questions of what does fairness mean and how does the domain depend on it and what biases are we encoding in data and kind of all these big questions, which of course directly impact our work. Now kind of distilling that into something that we can work with in an algorithm, that's still a big step, but we need to have that context first.
Hi, another question, me again.
Yes, please.
I guess I was in line with what Irene was asking. I was wondering if you've had any engagement from some of the real advertisement systems, just especially given your empirical results that show that the revenue the difference in revenue doesn't really change much. So it would be more beneficial to use your technique than the normal technique. So yeah.
I have not. I would love to. If you know anyone or anyone is willing to talk to me, I'd be more than happy to talk to them. It's yeah, I think it's from my experience, it's a little bit hard from talking to others who have also looked at these problems. It's a little bit hard to engage right now directly with companies, just because they've been under a lot of scrutiny, which I think is good and is important, but they're also a little bit wary of engaging with people who are not inside the company and therefore can say all kinds of things like, oh, hey, you're discriminating. So they're a little bit concerned about that, unfortunately. So yeah, it's certainly something that is needed. Again, if you know anyone, I'm happy to talk to them. But it's unfortunately not something I've managed to get to work yet, although I'm hoping it'll still happen in the future. We certainly have, yeah, so kind of a side note, on certainly in other domains, we have taken things to practice. So kind of this framework approach in a voting context, we deployed recently at a primary election in Switzerland, and there's kind of other more general things that we've talked about, various companies and nonprofits and things like that. But in this particular ad space, we've not been able to.
I'm also wondering, related to what you said, for engaging with people who work on different domains and grounding the work in fairness with different disciplines for which this is also extremely, maybe even more relevant. What are some good ways that you found to do that? Is it more natural to find it through a university to engage with different departments, or do you have any suggestions on like how to do that well?
Yeah, that's a great question. So I think more places have various kinds of data programs or data initiatives or things like that, and that's in some ways where they've already started kind of bringing in interdisciplinary voices. So at a particular university, that might be a good place to start to look through people there and see, kind of just see what they're up to, look at what kind of talks they have scheduled and things like that. Really at Yale, I just kind of cold call people and say, hey, you're doing something that is super relevant. Can we go have a coffee? And I think people are generally very, very open to it. And then even just asking those people, hey, who else do you know that I should talk to? And of course, not everything turns into a collaboration, but it's certainly very interesting conversations that I think are worthwhile to have, even if nothing more happens after that. And slowly over time, I think these connections get built. And the next time, that I have a really interesting question, I know the kind of set of people who might have something to say about it, right? And reaching out the second time with something specific is a lot easier if you made some kind of point of contact earlier. So yeah, it's not like there's anything very specific, but I think it's just a matter of building those connections over time and just keeping an eye out for who might have a different perspective on the same problems that you really care about.
Great, thank you.
Thanks.
All right, are there any other questions or comments? Okay, if not, thank you so much, Professor Celis, for taking the time to talk to us, and thank you for everyone who's been engaged with the, for participating in the colloquium, for asking questions and being engaged with us. And we're hoping to keep in touch. And thanks again.
Thanks so much for everyone. Yeah, please feel free to reach out later if you have any comments or questions or anything like that come to mind. And thanks so much for having me. It was great.
Thank you.
Thank you.